All right, so far we've been focusing our work on working with algebraic functions. These are functions where we will be raising x to a power or some expression with x to a power. So we got like polynomials, radical expressions, maybe we're multiplying, dividing, or adding and subtracting. Those are algebraic functions. Now we're going to move our focus to transcendental functions. And these are functions like trigonometric functions, exponential functions, and logarithmic functions. So we're going to start by just looking at the sine and cosine functions. We have two new formulas to learn. The derivative of sine is equal to cosine. So the derivative of sine of some stuff, sine of u, is cosine of u times du dx. So, you know, this is what we already know as the chain rule here. So the derivative of sine x is just cosine x, but if I'm taking the derivative of sine of some stuff, I'll use the same rule. I just gotta follow through by multiplying by the derivative of the stuff. With cosine, the derivative of cosine of u is the negative sine u, and then of course still have the chain rule in effect. So let's do an example. Let's say we want to find the derivative for the function y equals sine 2x. Well, now the way that you'll see these functions written will appear just like this. I usually add parentheses around the argument. I like to just make it really clear, okay, this is the argument, this is the stuff inside my function. So I add the parentheses myself most of the time. So here's a sine of 2x. So dy dx, using that first formula, this will be cosine of 2x, right? So cosine of the same argument. And then the chain rule says I have to multiply by 2. So we have 2 cosine 2x for dy dx. All right, so in our next example, we've got sine 2x times cosine of x squared. Again, I'm going to start just by kind of emphasizing, you know, 2x is the argument inside the sine function. X squared is the argument inside of the cosine function. And we're multiplying. So, you know, I could see certainly I've got some trig functions, right? I've got the sine function, I've got a cosine function involved. Overall, the structure of this function is that I'm multiplying these two things together. So this is a product rule problem. So that's what I'm going to work on first, is setting up the product rule. So my first factor, f, is equal to sine 2x. And so that means that f prime is the derivative of sine 2x. That's the one we just found in the last example. So that's 2 cosine 2x. Our g function is cosine of x squared. So g prime is, well, now I'm going to go back and use this second formula. The derivative of cosine is negative sine. So negative sine x squared. And now the chain rule says I have to multiply by the derivative of x squared, and that is 2x. So simplifying this a little bit, minus 2x sine x squared. Now the derivative of our function, dy dx, we're going to apply the product rule, so that's g f prime plus f g prime. G times f prime, that's the product of those two things. And so that is going to be cosine x squared times 2 cosine 2x plus f times g prime. We're going to multiply these two things. Sine 2x times negative 2x sine x squared. Now I'm going to clean this up a little bit, putting, you know, constant factors in front as coefficients. So 2 cosine x squared cosine 2x minus 2x sine 2x sine x squared. And there's our expression for dy dx. When we find derivatives, we always want to simplify. When we are finding derivatives and, our result involves trig functions, sometimes what we need to do to simplify is apply an identity. In this case, there isn't one, but for this, factor of x here, we would be able to apply one of the sum and difference formulas for sine and cosine. Probably actually the sum formula for cosine to simplify, but that factor of x right there kind of ruins our plans for doing that. So I think this is about as simple as this one gets. Let's try another one. We want to find dp dt. Here our function is p equals 25 times cosine squared of 120 pi t. So again, 120 pi t, that's the argument inside of cosine. And cosine squared here, that means that we're squaring the whole cosine function. So I'm going to rewrite this first. My function is p equals 25 times cosine 120 pi t all squared. And the reason that I'm writing it this way is it's going to make it easier for me to recognize what its basic structure is that's going to govern how I start taking the derivative. Yes, I could see there's a cosine function. I'm obviously at some point going to be taking the derivative of cosine, but that's not its overall kind of outer structure. The structure of this function is that I've got some stuff that I'm squaring. This is a power rule derivative, first and foremost. So dp dt, applying the power rule, right, I bring the 2 down in front, I multiply it by the 25 that's already there, I get 50 times cosine 120 pi t, right, the stuff to the 1 less power. So normally we'd write this into the first, but usually we don't write it if it's just to the first power. And now we have to apply the chain rule. So the chain rule says I have to multiply by the derivative of what was inside the stuff being squared, right? The stuff being raised to a power. So this is the derivative of cosine of 120 pi t. So that'll be a minus sine of 120 pi t times, and I have to apply the chain rule again, right? The derivative of cosine 120 pi t is minus sine, and then we apply the chain rule, we have to multiply by the derivative of what was inside the cosine function. So that would be 120 pi. So here we see, when we work with transcendental functions, we probably really see for the first time how the chain rule really can involve many layers, right? You could see how it really is like a chain with multiple links. So this function is like, you could think of functions as one of those, a set of those nesting, Russian dolls. I've got a 120 pi t function stuffed inside a cosine function, stuffed inside a squared function. And so when we take the derivative, we end up with multiple layers. So now we have taken the derivative. There's no more chain rule to apply. We need to simplify. So I'm going to multiply, let's see, I'm going to figure out 50 times 120 is 6,000. So we have a negative 6,000 pi and then we have sine 120 pi t cosine 120 pi t. So this expression is equal to the derivative. We can simplify a little bit though. In fact, here's a great opportunity to simplify using a trig identity. So the double angle formula for sine. This looks like sine of 2 alpha equals 2 sine alpha cosine alpha. So if I'm looking at an expression where I have a product of sine times cosine and the arguments inside are the same, then we can simplify using this double angle formula. I'm going to do one step in between. I'm going to rewrite this derivative we have as a minus 3,000 pi times, I'm basically just peeling off a factor of 2 sine 120 pi t cosine 120 pi t. And I can rewrite this using the double angle formula. So we're using this identity in that direction. I can replace that with sine of 240 pi t. So we end up with minus 3,000 pi sine of 240 pi t. This is generally considered more simplified because I can write it using just one trig function instead of two. All right, so we've been getting some practice, right? Learning these two new formulas. And, you know, when we want to make things a little more interesting, we say, let's try an implicit derivative. So here we have this equation kind of defines an implicit relation between x and y. We want to find dy dx. So here's our equation, x times cosine 2y plus sine x times cosine y. We have two terms, right, that we're adding together, but each of these is a product. So we've got product 1 and product 2. We're going to do a little side work to set up these products. For product 1, our f function is x, and that means that f prime is just 1. Our g function is cosine 2y, and so our g prime is, the derivative of cosine is negative sine, so this will be a negative sine 2y, and the chain rule says multiply by the derivative of 2y, so that'll be a 2 dy dx, because we are, of course, respecting x, right? We're finding dy dx in this problem. I'm going to clean that up just a little bit, say minus 2 dy dx sine 2y. For the second product, our f function is sine x. Our f prime function is cosine x. No chain rule to worry about, or at least the chain rule would say just multiply by 1. The g function is cosine y. So g prime is negative sine y, and then the chain rule says multiply by the derivative of y, but that's dy dx. We are respecting x. All right, so let's put this together. When we take the derivative on both sides, we first have our two products, so these are both going to be a gf prime plus fg prime equals, and then of course the derivative on that side is 0, because the derivative of a constant term is 1. G times f prime, for our first product, g times f prime is cosine 2y times 1. So I'm going to kind of move down here so I have a little bit more space. Cosine 2y times 1 plus the g times, f times g prime. So that'll be cosine 2y. Oh, no, sorry. That'll be f, which is x, times negative 2 dy dx sine 2y. Okay. All right, so there's our first product, g times f prime plus f times g prime, plus our next product is, let's see, in product 2, g times f prime. So we'll multiply those two things. We get cosine y cosine x plus, let's see, fg prime sine x times a minus sine y dy dx. Of course, that's equal to 0. All right, we have done kind of the first phase of this problem, right? We've differentiated both sides. We now have an equation that we could solve for dy dx. I'm going to start first just by cleaning this up a little bit. So our first product here, we got cosine 2y minus 2x dy dx sine 2y plus cosine y cosine x minus minus dy dx sine x sine y. So we want to solve for dy dx, and I'm going to start by just getting those terms on the other side of the equation so that they're by themselves. I'm going to add 2x dy dx sine 2y to both sides. And we're going to add dy dx sine x sine y to both sides. Let's see, what we are left with on the left side is cosine 2y plus cosine y cosine x equals, on the other side, dy dx sine x sine y plus 2x dy dx sine 2y. Now we can factor out the dy dx on the right side. And now it's all over but the shouting. We're just going to divide by sine x sine y plus 2x sine 2y. So now our result, finally, is dy dx equals cosine 2y plus cosine y cosine x over sine x sine y plus 2x sine 2y. And, you know, we find, like we did in the other implicit differentiation problems, you know, when you start out with an equation where kind of x's and y's, we can't get y as a nice neat function of x. So we're not really surprised that dy dx has to be an expression that involves both x's and y's together, and they can be sometimes a little bit cumbersome. But the process is basically the same. You differentiate both sides with respect to x. You gather all of your dy dx's on one side, so that you can then factor that out and then divide and get your expression. The only thing different in this case is that we're learning to do this in equations that involve the sine and cosine functions. Alright, we're going to do one more example. We're going to find dy dx for the function y equals tan x. It's a simple function, right? Tan x. It's just a plain old x inside, so it's not like I'm going to have to worry about the chain rule at all. But we don't, at least not yet, we don't have a formula for the derivative of tangent. So what we're going to need to do is rewrite this. And this problem becomes a lot easier when we just realize and remember that, well, tangent is equal to sine over cosine. So I'm going to rewrite the function as sine x over cosine x. Now I can apply the quotient rule to this expression, and I know the derivatives of sine and cosine. So let's sort of set ourselves up for that. Our f function is sine x, which means f prime is cosine x. Our g function is cosine x, and that means that g prime is negative sine x. So dy dx, we're going to use the quotient rule, so that's g times f prime minus f times g prime all over g squared. So g times f prime is cosine times cosine. Cosine x times cosine x minus sine times a negative sine. So sine x times negative sine x all over g squared, so that's all over cosine squared x. Alright, let's clean this up a little bit. Cosine x times cosine x, that's cosine squared x. We're subtracting a negative product, so it'll be a plus sine squared x all over cosine squared x. We are all, of course, resisting the temptation to cancel. We all know that we're not allowed to cancel over addition, so those cosine squareds do not cancel. However, up top we've got cosine squared x plus sine squared x, and Pythagoras tells us that cosine squared x plus sine squared x is equal to 1. And 1 over cosine squared is secant squared x. So our derivative is secant squared x. Now we've done more than just find the derivative of tan x. What we've done is really we've shown that generally, we've shown the general rule that the derivative of the tangent function is secant squared function. And we can extend that rule for tangent of anything as long as if we apply the chain rule. So we just showed that the derivative with respect to x of tan u is secant squared u times du dx. And so there's a formula that we can just use. Now if we forget that the derivative of tangent is secant squared, well, we can always get to it again. You know, if I know the derivatives of sine and cosine, I can rebuild that. Kind of sort of derive this fact. So that's going to finish up this section. And we're going to look at the derivatives of the other trig functions in the next section. And we'll sort of see this formula can make an appearance there.